So in this video, we're going to talk about a set of rules which are referred to as Demorgan's rules, or some refer to them as Demorgan's laws. And this will become very useful when it comes to probability theory, when you get to that point in your education here. So with Demorgan's rules, the whole idea is what happens if I take the complement of A union B? Is there a way to simplify this? Well, let's do this visually to see if we can find an interesting rule to help us simplify this. Suppose I have two sets. I have set A and I have set B. And suppose I have some elements in each one. Okay, so let's look at it. And suppose I have some elements outside. Okay, so I have A union B, which are all the elements in the circles here. I want to know what's outside of those circles. Well, if you notice, this is A, and this is B here. What is outside this union of the two sets? Well, I have three data points that are out here, and you'll notice that this data point and this one and that one as well. That one's not in A, right? So we know that all of these three data points are definitely not in A. So they're definitely in the complement of A. But here's what's also interesting. They're also not in B. And so as it turns out, these right here, these points, which are not in A, and they're not in B, they're actually in the intersection of the complements, right? Because think about all the elements that are not in A. It's this element, but it's also this, and this element. But these elements are clearly in the union. So how do we tell, basically our math here, how do we tell using our math that these data points are not in A? Well, we also say that it's not in B. And when we look at the intersection of not in A and not in B, we get an interesting rule here. That is, we can rework the complement of the union of two sets as the intersection of their complements. And this should not be too hard to see. Look at all of the elements that are not in A. Those would be this, and this. And look at all of the elements that are not in B. This, and this. We can see that when we intersect the complement of A and the complement of B, we get very simplistically the three right here. So when we look at the opposite, by the way, I'll leave this as an exercise for you to show. When we take the complement of that, we actually get the complement of the union of the complements. So what's another way of writing, this is the intersection between A and B. The question is, what is the complement of the intersection of A and B? Well, again, look at it visually. I'll let you do this as an exercise for yourself. But when you look at this visually, you may notice that you get the same thing that's on the right-hand side. Now, Demorgan's rules become very important in probability theory when we're looking to try and understand the outcomes of certain events, and we'll get into all of that at a later point in time. They also help us further reduce statements. So, for example, if I have A complement intersected with A union C complement, one way to simplify this is to take the C, right, just like we have here, and convert it to something like this. A complement intersected with A complement, right? Turn this to intersect C complement. And A complement intersected with itself is just itself, right? A set that's intersected with itself is just itself. just like a set that's unions with itself is just itself. So we end up just getting A complement intersect C complement. But what do we get with that? Interestingly enough, you can use Demorgan's rule to reverse it. You'll notice we get the opposite ruling here, which is to basically rip the complement out and turn that C over. So we get A union C and the complement of it. Okay, and so there you have it. We had used Demorgan's rules to simplify a more complex expression.